Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the lecture number 14 for the course of Communication Technology. My name is Engineer Jaffar and I am an instructor for this course. So as you all know, this is our lecture number 14, and in previous lecture we discussed about the pulse amplitude modulation. Actually, in the last two lectures we have been discussing about pulse amplitude modulation. It is the one of the kind of pulse modulation, and in this coming lecture we are going towards this PDM and PPM. PDM is basically pulse duration modulation, also known as pulse time modulation, and the second one is pulse position modulation. These are the further two subclasses of pulse modulation except from pulse amplitude modulation. So let's talk about PDM, or you can say this PTM. This is pulse time modulation, and in this pulse time modulation, amplitude of a pulse is kept constant, and the position or the width of the pulse is made proportional to the amplitude of signal at the input, or you can say at the sampling instant. At that point of time, this output depends upon amplitude of the signal. So it can be PWM or PPM. PWM is basically pulse width modulation, and PPM is a pulse position modulation. Now you can take an idea from these wordings: pulse width modulation and pulse position modulation. In both these cases, the amplitude is constant and amplitude does not have any information. So amplitude limiters can be used, just like in FM. If you recall the FM scenario, in the FM or frequency modulation, the amplitude and the phase were the parameters that were kept constant, while only the frequency was changed in according to the input amplitude. Similarly, in this pulse time modulation or pulse width modulation and pulse position modulation, amplitude limiters are used, just like in FM. So just like in FM, there are two methods for this generation of pulse time modulation. There were two methods for generation. One was direct method and another was indirect method in the frequency modulation generation. In correspondence to that, indirect method and direct method are also used in the generation of PTM signals. Excuse me. So in the first indirect method, in the first step, PAM signals are generated, and it is then synchronized during each pulse interval. These two signals and then are added up, and the sum is basically given to the comparator. And there is a comparator, and comparator has a reference level, and that reference level is used to determine whether to go which side of the generation part. The second crossing of the comparator level is used for the PPM or pulse position modulation. The second step is basically the direct method. So in the direct method, waveforms are generated by use of this PM waveforms. Let's talk about PWM. The pulse width modulation is a kind of modulation in which the modulation of the signals is basically done by varying the width of the pulse instead of the amplitude. The amplitude and the position of the pulses are the factors or the components that we keep constants while doing a pulse width modulation. So this is an example of generation of PWM and PPM by direct method. In the first diagram, you can see that you have, let me show it to you. So this is the setup why you do this PDM or PWM and PPM. So in the first step, there is an input signal, and there is also a sawtooth generator, and this is a comparator. It generates a difference value, and this difference value is basically then given to the PDM or PWM, and it is also used by a single entity of monostable, and it is basically it converts into PPM, pulse position modulation. Monostable is a kind of temporary buffer, you can say. It holds up to a certain time. That is also customized It is also been made customized as per the requirement. But let's talk about the sawtooth. So this is the sawtooth generator. You can see that this is the sawtooth generator wave, sawtooth wave. This is basically produced by a separate generator, and this is your PDM. You can see that pulse duration modulation. The duration of the pulse, or you can say the width or the time of the pulse, is basically differentiated. You can see that this is of a different time, this is of different time, this is of different time. All of these are varied in respect of their times or their width. So this is pulse duration modulation. In the next step, this is the pulse position modulation. You can see that pulse position modulation is used used after a buffer, or you can say monostable, that is a temporary buffer, and you can see that the position is continuously changed in the first periodic time, or you can say the symbol time period, or symbol period. It was initiated after this point of time. Let's say this is 0.1 second. Let's call it 0.1 second. In the second periodic symbol period, you can see that it is generated or at least twice of the double. So let's say this is 0.2. So you can see that the position of the pulse is being changed. In the third symbol, it was at the end. Similarly, in the fourth and the fifth, the only difference in all of these is the time of the initialization of that pulse. So this is your PPM wave. Similarly, you can have a clear idea about the sawtooth. This is your sawtooth wave. This is basically mixed with the comparator, which has an input. Let's say this is your input wave, and these are your three. This is your PWM, and this is your PPM, and this is your inverted and differentiated wave. When you multiply this signal, input signal, compare this signal with this signal, you can see that this is the comparator, which basically creates a differentiated value, and this value is then basically fed up to the PDM or PPM as per the requirement of the system. So the non-inverting input of a comparator is fed to the input message signal or modulating signal x of t, and the output of by a sawtooth signal which operates at the carrier frequency. The comparator compares the two signals together to generate the PWM signal at its input. Normally the input is high only when the instantaneous value of the input signal x of t is higher than a sawtooth wave form. The rising edges of the PWM signal occurs at the fixed time period kt of s, and you can see that this k is basically a factor which is a constant k, and it is basically nothing but a periodic representation of a periodic signal, while trailing edge depends on the amplitude of the message signal x of t. When sawtooth waveform is generated waveform is greater than x of t, output of the comparator is 0 and trailing edge is modulated. If sawtooth waveform is reversed, as we saw in this diagram, you can see if we reverse it or we invert this, so the trailing edge is fixed while leading edge is modulated. So you can do the both of these things. If you take the first form, you will be modulating the trailing edge, and if you reverse it, you will be modulating the leading edge. Similarly, replacing sawtooth wave by a triangular wave, both leading and trailing edges will be modulated. So you can use if you want to use both of these edges to be modulated, you can use triangular waveform despite of this sawtooth waveform. And a triangular waveform is something not much different from a sawtooth. So you saw the sawtooth waveform. This is the sawtooth waveform, and triangular waveform is something like this. It is symmetrical on both hand sides, whereas a sawtooth waveform is not symmetrical on both hand sides. If you cut it in the half, it is not symmetrical on the both hand side, while if you triangular wave, if you cut into half, you get a symmetrical wave. So these three types of pulse width modulation are possible depending upon the edges and the shape of the sawtooth. The first one is when the leading edge of the pulse is being constant and the trailing edge varies according to the message signal. In the next case, the trailing edge of the pulses is being constant while the leading edge varies according to the message signal. The third case is a unique case in which the center of the pulse is being constant while both the trailing end and the leading edge are varies according to the message signal, that is symmetrical PWM. So if you also want to use this sawtooth waveform, but you also want your PWM signal to be symmetrical, you can use this kind of system setup in which the center of the wave is being kept constant while the trailing edge and the leading edge are varied according to the input message signal. So this is the kind of scenario in which this was the carrier pulse, and you can see this was your modulating input signal. So this is the first case in which the leading edge of the pulse is constant and the trailing edge varies according to the symbol that is fed into the system. This is the second case in which the trailing edge of the pulse is kept constant while the leading edge varies according to the input signal, that was your modulating signal or your message signal. And in the third case, the center of the pulse was kept constant while the leading edge and the trailing edge were varied according to the input of the signal, or you can see the your modulating signal. Let's talk about indirect method. So in indirect method, modulating signal, let's say A, is applied to the input of a PWM circuit, and this is not a single signal, it is basically a pulse train, and a PWM signal generated B, let's say S of t is your message signal, and it is also applied to the input of the ramp generator, all these having slopes, amplitude and generation D. Then the next step, the ramp is basically ramp pulses are added to the PWM pulses to produce varying height samples, and these varying height ramps get short circuited to generate varying different width rectangular pulses of PWM. So this is a kind of setup in which you can see that there are three main blocks. The first one is PWM generator, the second one is ramp generator, and the third one is schematic trigger. And this is nothing but a summer. Summer is a point where you basically sums both of these input signals. So this is a summer, and you have this A, this is your X of t, and this is your carrier, or you can say the message signal, the another signal, that is S of t, and you basically add them. But before adding, they have to move. They have to fit into a different modules. The first one is PWM generator, and the second one is ramp generator. And after that, you provide the input to the schematic trigger, and then you can generate the PWM, or you can say the pulse width modulation signal. You can see that this is not a direct approach. In the direct approach, we use the signals directly to perform the operation, but in this indirect method, they are not directly added, but instead of directly adding, you are giving the inputs to a PWM generator of which takes the input of X of t, and the ramp generator which is taking a signal S of t, and then you add them. So this is the indirect method. So this is the working of the PWM detector. So you can see that all of these blocks are already there. The first one is schematic trigger. It was there at the transmitting end side while you were generating the PWM signal using an indirect method. There is also a ramp generator, there is also synchronization pulse generator, and there is also adder, and there is also level shifter. A level shifter is a new term for you, I hope so. If you have heard about this, well and good. If not, I will tell you in a very brief points. So, but we will also discuss that in the class as well. Level shifter is a type of, you can say, if you recall your last semester's course of microprocessor, you will have an idea about left shift resistors and right shift resistors. Similarly, there is also a level shifter, and the purpose of this level shifter is to basically manipulate the amplitudes. You can see that, let's say this, you can clearly see that these are the same pulses, but the only difference is their level. This level is the first pulse is generated from this level, the second pulse is generated from this level, and the third pulse is generated from this level. So there is level shifters given to the signal. After that there is a rectifier, and in the end this is low pass filter. All of the terms are basically discussed in somewhere or other during the course and in the previous semester as well. So I hope that this won't be much difficult for you to understand. Let's talk about pulse position modulation. Pulse position modulation, commonly known as PPM, is an analog modulating scheme in which the amplitude and the width of pulses are kept constant while position of each pulse is changed, as we discussed earlier, with reference to the position of a reference pulse varies according to the instantaneous value of the message input signal. So the transmitter has to send synchronizing pulse, and the importance of synchronization is no much of further discussion. You already know its importance, that what is the importance of synchronization in the pulses, and to keep the transmitter and receiver at the synchronism. These pulses, these sync pulses, help to maintain the position of the pulses. PPM is done in accordance with the PWM, as we discussed in the previous diagrams, that how you can use a monostable to use the PWM signal and convert it into a PWM signal. PWM signal is used as a trigger input to a monostable multi-vibrator, and its output remains 0 until it is triggered on a trailing edge of PWM. Output of monostable, that is known as MV switches to a position to positive saturation value A, and remains high for a fixed position or fixed period of time. Then it goes low. Hence the position of these pulses is proportional to the width of the PWM signal. So you can clearly have an idea about the relationship between the PWM signal and this PPM signal. So there are quite advantages and disadvantages of using this PPM. So the major advantage of using PPM is that as the amplitude and width are constants, the power handled is constant. So there is not of much power required, because the amplitude and width are kept constants. The only thing is basically the position. So the power factor, you have basically have controlled power expenditure or expense. But the disadvantage, which is not that much of disadvantage, the disadvantage is basically the complexity required to synchronize the transmitter and receiver. There is a complexity level up to which you can bear, and this is not a much hectic task. Synchronization nowadays is not that much of a difficulty because of the development and upgradation of different tools and softwares and techniques that are there to synchronize the transmitter and the receiver. So these are the pros and cons of using pulse position modulation. The pulse duration modulation is differentiated and then rectified and then shaped. PPM carries the same information as long as the position of the clock pulses is well defined and in the received signal. PPM is superior to PDM for message transmission signal, while pulses of PDM required more energy than PPM when transmitted. So I have discussed you, if you have your duration of the pulse is basically enhanced, your energy is going to be enhanced. If your energy, you want to control the energy or the power, you have to use PPM. PPM is most suited for the communication in the presence of noise, because the lesser the signal or the lesser the position, the lesser the width, the lesser the chance of the or the lesser the probability of the noise to damage the signal. PPM, very high peak narrow pulses can be transmitted, and the pulse position can be determined even when the and the noise level is quite high. You can easily detect. However, the transmitting very narrow pulses requires a larger bandwidth. So if you are basically reducing the time, because the time position in the pulse duration modulation, if you reduce the time, so you are in the frequency domain, you are expanding the frequency. It means that the bandwidth requirement has been raised. So you have to keep in mind that your pulse should not be that much narrow so that you exceed your bandwidth threshold. When the light is used as the medium for transmitting analog signals, PCM or PPM are the most suitable types of modulation, because the maximum power outputs in the modulated light source such as LED or laser is achieved when every pulse is at low duty cycle. Last point is that in PPM it is necessary to transmit a series of sync pulses at a much lower repetition rate than a sampling pulses, and this is done to avoid the original signal to have any interference or with any other signals, or to minimize the number of pulses required to transmit it in order to conserve the transmission power. You see that these terms are kept repeating itself again and again in different terms and forms. Transmission power, efficiency, energy efficiency, these are all interrelated, so you cannot differentiate or distinguish these terms from one another. These are interrelated terms, so you have to bear with it. Let's talk about the transmission bandwidth of the PWM and PPM. So both have a DC value. Both this PWM and PPM is DC value, and both need the sharp rise time and a fall time to preserve the message information. Rise time be very less than the transmission period, that is TS, and the bandwidth higher than this. We will discuss that in the this slide. When we come in the next slide, you will see. So let's compare this recall this all of these modulation techniques of pulse modulation that we discussed. The first one was PAM, in which the signal of a pulse is proportional to the amplitude of the modulating signal, and the bandwidth of the transmitting channel depends upon the width of the pulse. Instantaneous power of the power transmitter varies, and the noise interference is high. It is a complex system and it is similar to AM. The next one was a PWM, in which the width of the pulse is proportional to the amplitude of the modulating signal. The bandwidth of the transmitting channel depends on the rise time of the pulse, and the instantaneous value of the transmitter is also the power is varied, and the noise interference is minimum, similar to the implementation of FM, and it is also simple to implement. The last one is a PPM. It is in which the relative position of a pulse is proportional to the amplitude of the modulating signal, and the bandwidth of the transmitting channel depends on the rise time of the pulse. Instantaneous value of the power remains constant in this PPM, and the noise interference is minimum. It is also simple to implement, and it's similar to PM, or you can say phase modulation. So we started from AM, FM and PM in the midterm, and now we have come to the pulse modulation, in which we are also discussing PM, PWM and PPM, which are similar or to AM, FM and PM respectively. So let's conclude our discussion of these topics with the common table, in which there is a differentiated points with respect to different parameters. They are being differentiated. So all of these are discussed in some way or another in the last few lectures. So just go through it. If you have a type of carrier, so PM require a train of pulses, PWM also requires a train of pulses, and PPM also requires a train of pulses. If you are the parameter to be distinguished between is variable characteristics. So the only difference in the PM is that amplitude varies, in the PWM the width varies, and in PPM the position varied. If it comes to the bandwidth requirement, PAM required low bandwidth, PWM require higher bandwidth and PPM require higher bandwidth because the time is basically limited, so the bandwidth is increased. If you talk about noise immunity, PAM has low immunity against the noise, PWM has a high immunity against the noise, and PPM has a high immunity against the noise. If you talk about the information contained in the information contained in PAM is basically in the amplitude variations. In the PWM, the information is contained in the width variations, and in the PPM, it is the information is contained in the position variations. If you talk about the power efficiencies, the SNR or you can say the signal to noise ratio of PAM is basically low in PAM, and the signal to noise ratio is moderated in PWM, and signal to noise ratio is very much high. You can say a good thing is that PPM provides you a maximum signal to noise ratio. So it means the noise, it has a highest immunity against the noise as compared to the PWM and PAM. When you talk about transmitted power, so in PAM the transmitted power varies, in PWM transmitted power is also varies, and in PPM you have a clear idea, because you have clear idea that my pulse has a same amplitude and width. The only thing is basically the time, so it has a constant power, transmission power, or power energy consumption over all of the time. If you talk about the bandwidth requirements, so it depends upon, in the PM it depends upon the bandwidth or the width of the waves or the pulse. And the PWM, the bandwidth is basically dependent upon the rise of the pulse, and in the PPM it also depends upon the rise time of the pulse. If you talk about the transmitter power, so instantaneous power varies with the amplitude of the pulses. In PWM it varies according to the width of the pulses, and in PPM, because of the both of these factors, that is amplitude and width, is constant, so it is also constant. You can see that this is also constant. Now let's talk about the complexity of generation and detection. So it is in the PM is complex, PWM is easy, and PPM is also complex. And similarity with other modulation systems that we discussed in the previous portion of the course series in midterm, where we started AM, PM and FM, we come back to the point that PAM is similar to the AM, PWM is similar to FM, and PPM is similar to PM. So let's go to the last slide. Let's finish our lecture with our discussion of this all of these pulse modulation techniques with numerical. So let's say there is a PAM transmission for a voice signal with a maximum frequency of 3 kHz. We have to calculate the bandwidth that is required for the transmission, given that the sampling frequency is 8 kHz and the pulse duration T of 0.1 T of the symbol period. So you know that the symbol period is inversely proportional to the frequency of sampling rate. So if it is given that TS is equal to 1 by Fs, so you can easily find that this TS turns out to be 125 microseconds. As you already know that T is equal to, it was mentioned that tau is equal to 0.1 TS. So you just put the value of TS over here and you will get the value of tau, which is 12.5 microsecond. Now if you recall, the bandwidth requirement was at least 1 divided by 2 tr. It is 1 divided by 2 tr. So it was this was the equation, and it should be greater than 40 kilohertz, because if you put the value of 2 tr, so you will divide it by this thing and you will get 1 by 40 kilohertz. For above signal, if the rise time is 1% of the pulse width, find the maximum transmitted bandwidth for PWM and for PPM. So similarly, you know that this tau is equal to 1 divided by 2 tr, that is the rise time, twice of the rise time. So if you put the value, if you want to find the value of the rise time, you can easily use this equation, the value of tau is 40 kilohertz, and if you multiply it with the 1%, that is 0.01, you will get this equation. This is the rise time. You got the rise time, and if you want to find the bandwidth, you just, sorry, this is misprinting over here, this is over here. So the bandwidth, if you multiply 2 with this equation and divide by 1, you get 4 megahertz of bandwidth. So the bandwidth requirement for the PWM and PPM signal is much higher than PAM. You can see that the bandwidth requirement is 4 megahertz over here, and the bandwidth requirement was about 40 kilohertz over here. So here it is about 100 times more than the previous one. So this is all about today's lecture. I hope that you have learned quite a lot from this lecture, and if you have any questions, you can write it down so that you won't forget it to ask that question in the class. And I will highly appreciate if you bring some good questions to the class, because you know that the more you ask, the more you learn. Thank you very much. I'll see you in the class. Allah Hafiz.